Stanford University.
So, welcome back everyone. The sign-up sheet is wandering around if you haven't yet signed up. Sometime within the next couple of days, I was away at the end of last week. I was in Baylor University in Texas and didn't have time to do this. But sometime I'll go through the list and see those of you who want to do this for credit, and I'll send out an email and we'll sort of start some negotiations about what kind of work you're interested in doing to do it on a credit basis. And I want to pick up on a theme that we just really touched upon last time when I was talking about the introduction of numbers to Western Europe, modern Hindu-Arabic arithmetic, and mentioned that Leonardo of Pisa in his mammoth book Liber Abaci had this little throwaway problem about rabbits that gave rise to this whole cottage industry about building up beliefs about the Fibonacci numbers and a rather interesting related number, the Golden Ratio. Now, unusual for a course like this, there's actually a quiz, and I'm about to give you the quiz, but it's going to be a self-graded quiz. And as we go through the lecture, the first part of the lecture, I'm going to tell you the standard story about the Golden Ratio and the Fibonacci numbers that you can read in books and websites as much as you want. In fact, if you go back to anything I wrote over about 15 years ago, you'll find the same claims made in my books and articles. If you go back onto the NPR archives and listen to when I talked about the Golden Ratio many years ago, you'll find I made certain claims. And it's not altogether clear that all of those claims are true. So as we go through the lecture, the first part, which is the standard story, what I want you to do is just mark off whether you think each one is true or false as we get to it. And then after I've gone through the standard story, we're going to pause, take our breath, and then I'm going to go through and examine all of the various beliefs and claims about the Golden Ratio and the Fibonacci numbers. And there's a lot of them. Okay, this is one of those places where mathematics, some of it very interesting pure mathematics, some interesting results in number theory to do with the Fibonacci sequence. So we're going to have a place where mathematics, real mathematics, meets sort of popular culture. And when that happens, strange things can occur. So this is the facts versus fiction. We're going to try and tease apart among these beliefs and claims about the Golden Ratio, which ones are true and which ones are false. And then we're also going to do a little bit of experimental work ourselves to just see if we can get some empirical evidence that would support whether something is true or false. So the number right on the top is the first few decimal places of this irrational number, the Golden Ratio. Already that's kind of interesting because a ratio is rational and this number is irrational. So the Golden Ratio is actually not a ratio of numbers in the sense of whole numbers. It's a ratio of lengths.
Can you explain the difference between rational and irrational?
Oh, a rational number is just one that's a quotient of two integers, two whole numbers, one divided by the other. So any number which is obtained by dividing one whole number by another whole number is a rational number. And until the time of the Pythagoreans, it was assumed that all numbers were rationals, because you can by taking big enough denominators, you can make numbers as accurate as you want for measuring things. And indeed, the rational numbers are certainly adequate for measuring things. In fact, you usually don't need a denominator more than about 100 or so in order to measure things quite accurately. But then there was a discovery made by one of the Pythagoreans that if you take a right-angled triangle whose sides adjacent to the right angle are 1 unit, so that by Pythagoras' theorem, the hypotenuse is the square root of 2. You've got hypotenuse squared equals the square root, this is sum of the squares of the other sides. So you've got 1 squared plus 1 squared. So the hypotenuse squared is 2. So the hypotenuse itself is root 2. And one of the Pythagoreans showed that the square root of 2 cannot be expressed as a quotient of two integers. In fact, just today when my online MOOC, my online course, this course with 61,000 students, when the video that went out today actually contains a proof of that ancient result. So just by chance on today's course, the students, so 60,000 students were able to see the proof that the square root of 2 is irrational. Okay, so and one of the features about irrational numbers is that their decimal expansion, because they're not a quotient of two whole numbers, their decimal expansion continues forever without settling into any repeating pattern. Like a third continues forever. It's 0.333 recurring, but there's an obvious pattern to it. Irrational numbers, there's no pattern emerges to the expansion. So if you continued that number on the top to generate this thing called the golden ratio, which we'll look at, then it will keep on, different numbers will keep coming up and surprising you all the time. The sequence at the bottom is the Fibonacci sequence that we met last time. And as we'll see today, those two numbers are actually very closely related, which tells you that this is more than just rabbits. There's something else going on that's kind of interesting. But and the symbol phi is a symbol that relatively recently has been used to denote the golden ratio. Okay. So let me tell you the standard story. And has everyone got a copy of the quiz now? Because you're going to grade yourself. I mean, you're going to put true and false in as you go through the lecture, and then after when we reach the pause, before I go through and examine them, if you've filled in all the T's and F's, then you can go through and grade yourself. Okay, and then we'll see if anyone can get them all right. Okay. Okay, so here's the standard story about the golden ratio. It's a great story. Okay. One of the ways of representing it or explaining it is to say, and the claim is that there's a rectangle whose aspect ratio the human cognitive system finds the most pleasing. So there's an aesthetic thing that the golden ratio is the aspect of a rectangle which the human eye finds the most pleasing. Okay, that's one of the claims made about it. That rectangle, and here is one of them sort of, the golden rectangle. The aspect ratio is known as the golden ratio, sometimes called the divine proportion. Okay. That goes back to Leonardo da Vinci's time. I mean, this terminology goes back a ways. So, three different terms, all talking about the same thing. And here's one way you can get it. Now, I mentioned that it's actually not, it's an irrational number, so it's not, in fact, the ratio of two whole numbers. It is, however, the ratio of two lengths. And what happened to the ancient Greeks is they were interested in geometry, so they were thinking that pairs of numbers, quotients of numbers, could measure all lengths. When they realized that wasn't the case, essentially geometry and arithmetic split apart. And so there were numbers, rational numbers, and you could do things with them, and then there was lengths. In fact, even as recently as the 17th century, when Newton invented calculus, or Newton and Leibniz invented calculus, it was actually applied to lengths, not to numbers, because it wasn't until the end of the 19th century that mathematicians finally fused together those two conceptions of numbers, the ones that came from our cognitive apparatus dealing with measurement and the ones that dealt with counting. And it was a rather difficult task to bring those together. Okay. And it occupies most students the whole first year of university, the ones that do mathematics, to go through the material that shows how those things come together. So here's one way you can get it. You divide a line into two so that the ratio of the whole to the larger part equals the ratio of the larger part to the smaller. So here's a picture, here's a line, and I'll choose my units so that the line has length 1. I'll split it up into a part that's x, and the other part is 1 minus x. Then the ratio of the whole, which is 1, to the larger part, which is x, equals the ratio of the larger part to the smaller part. Okay. This idea of doing this goes back at least to Euclid. This was in Euclid's Elements. Well, you can take that and you can rewrite that equation we've just seen. You cross-multiply. Well, this is like one of these Tom Lehrer things. If you're my age, you cross-multiply. If you're younger, you multiply the whole equation by x times 1 minus x. Okay. Rewrite that as x squared plus x minus 1 equals 0. Just do whatever you do to turn it into an equation. And then you solve it by either using the formula for the quadratic, or you use completing the square, or whatever your favorite way of solving the equation is. And we'll look at that in the second lecture. As with last week, there's really 2 lectures, and that's going to be the pattern for most of this term. Okay, you end up with this number 0.61803 approximately, and then the ratio, which I'll start using this symbol phi, is the ratio between the whole length and the x. So we've now found the x, we've found the long part, and so that's 1.61803. The decimal part repeats. Okay, so there's this thing, and it is irrational, it keeps going on forever. And it's irrational because of the square root of 5. Just as the square root of 2 is irrational, so is the square root of 5. Well, that's fine. That looks like the kind of thing you'd expect to see in Euclid's Elements, but there's very little in Euclid's Elements where a Google search will take about 4 million hits when you type in Golden Ratio. So this is obviously a number with a life of its own. As we'll see, this number is related to the Fibonacci numbers. And if you type in Fibonacci numbers, they're far less common, but you still get almost 1 million hits. Now, there are very few numbers that get this kind of attention. So these are clearly cultural numbers. They mean something to a lot of people. In fact, it's amazing what they mean to a lot of people, because if you start looking at some of those 4 million Google pages that Google, I mean, many of those hits take you to the same page, of course. But if you go through that, you'll come to pages like this. You'll see pictures of the pyramids, where there's a claim made that its aspect ratios are built somehow on the Golden Ratio. You'll see pictures like this, where golden ratios, golden rectangles are superimposed on the Parthenon. You'll see more detailed images like this. There's a larger picture of some of the pyramids. There's claims made that the Golden Ratio can be found discussed in ancient Babylonian texts. So these are all part of the standard story. You can find these claims over and over again. It's claimed that lots of modern architecture embeds the Golden Ratio. In particular, it's claimed that the General Secretariat building for the United Nations is 3 golden ratios stacked one on top of another. It's claimed that the human body has proportions in the Golden Ratio, that if you measure from the top of your head to your feet, and you measure from your navel to your feet, it's claimed that the ratio of those things is the Golden Ratio. Okay. It's claimed that you can find it all over the place in art, in Botticelli's Venus, and here's an image I grabbed from the web, where there's phi to the 7th, phi to the 5th. There's all sorts of golden ratios supposed to be in the proportion of that. It's claimed that Leonardo da Vinci was enamored by the number and embedded it in all kinds of drawings and paintings. Now, it's true that he was a close friend of Luca Pacioli, and he was the guy that used the term the divine proportion. So Leonardo da Vinci certainly knew about that number, and he knew about it from someone who thought it was a big deal. Now, the question is, did he actually do anything with it in his art? It's claimed that he does, okay, or that he did. It's claimed in particular that this painter, Georges Seurat, very strong claims are made about the fact that his paintings were built on golden ratios. There are certainly lots of rectangles floating around. It was claimed that many of them are golden rectangles. It's claimed that the architect who renamed himself Le Corbusier advocated and used the Golden Ratio. You'll find that claim made. You'll find it claimed that Virgil composed the Aeneid based on the Golden Ratio, to do with the meter. It's claimed that Mozart used the Golden Ratio in some of his music. It's certainly got a mathematical sense to it. It's claimed that Bartók used the Golden Ratio in some of his music. It's claimed that Debussy used the Golden Ratio in some of his music. It's claimed that the Nautilus shell, and I actually have a real one here, that is to do with the Golden Ratio. It's certainly a beautiful artifact. But, so the question we're going to be asking ourselves is, can you find the Golden Ratio in there? Actually, the answer is yes, but can you meaningfully find the golden ratio in there? That's another question. The reason I wanted you to bring the tape measure is we're going to have a little experiment later on to see how many times we can find the golden ratio. Okay. It's claimed that the golden ratio crops up all over in mathematics to do with the pentagon, the regular pentagon, the regular pentagram, that with Penrose tilings, which are irregular tilings of the plane, that it can be found in regular solids, that in fractals, the golden ratio plays a large role. There's all sorts of claims made about it in advanced mathematics, not necessarily just advanced mathematics, but sort of real pure mathematics. So this is real mathematics, and it's claimed that the golden ratio can be found all over there. It's claimed that there are some really interesting repetitive patterns that you can get with arithmetic, that if you start iterating square roots, and you can play this one on a calculator with a square root button if you want, you can sort of put in this thing and try to iterate it through, or that if you do a continued fraction, constantly adding 1 plus 1 over 1 plus 1 over 1, it's claimed that that's the case. Again, we'll have to ask ourselves if this is true or if it's just something that is close. Okay. It's even claimed that the golden ratio is in the Bible. Again, I've just taken this from the website where we've got the Ark of the Covenant and the Noah's Ark. Okay, so it's claimed that the golden ratio is really used all over the place. What about the connection with the Fibonacci sequence? Because we got onto this because we were talking about Fibonacci last week. I mean, this poor guy would be turning in his grave because he had nothing to do with it, and he'd wonder what the fuss was about. But this was his popular legacy. You know, last week I tried to explain what his real legacy was. So we talked about Leonardo last week and the rabbit problem, and that was the problem that was in the book Liber Abaci. And I can't resist, I'm not sure if these will show terribly well because this is a watercolour, but you can more or less see it. There's some beautiful drawings. I'll give you a reference to this in a minute because if you've got kids or grandchildren, this is a wonderful book to buy them. Here's the garden where the rabbit goes, and I guess that's a pregnant rabbit because she's knitting. And then we have some little baby rabbits in month 2, and then we have month 3, we get some more rabbits. And then month 4, we get some more rabbits. Then we get some more rabbits in month 5, month 6, and so on. I won't give you the whole 12 because I knew it wouldn't reproduce well on the screen. But this is a book by Emily Gravett called The Rabbit Problem. Delightful little watercolour illustrated book about Fibonacci's rabbit sequence. So definitely worth buying. I mean, actually, it's the kind of book that you buy for your grandkids because you want it, right? So. Definitely well worth looking at. Okay, and here's a graphical representation of the problem, that you've got this growth pattern of these rabbits. Each one has to wait 2 months before it reaches fertility and then starts producing pairs of rabbits. And you're counting pairs of rabbits when you do this, okay? So you've got 1 pair of rabbit, 1 pair of rabbits, 2 pairs of rabbits, 3 pairs of rabbits, 5 pairs of rabbits. And that gives you the sequence. And if you generate it further using a computer generation, you get this sequence of numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so forth. That's that sequence. And this sequence, the rule that generates it is that the new element, you're sort of going in groups of 2. So you go from 1, 2 beyond. The last element in the sequence so far is the sum of the 2 previous ones. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21. So you just add the last 2 each time and that gives you the next one. A very simple repetitive rule. This is what made it a nice problem for Leonardo to get people practiced in using Hindu-Arabic arithmetic, because they were constantly adding numbers. And they were adding numbers that were getting bigger, so they first of all had single-digit numbers, then double, then 2-digit numbers, then 3-digit numbers. So it was a nice way of dressing up learning how to do arithmetic. So we've got a simple recurrence relation that defines this. And the connection with the golden ratio comes about when you start dividing successive pairs of these things. So you've got the numbers 1, 2. Divide 2 by 1, you get 2. Divide the next one by 3 by 2, you get 1.5. Then divide 5 by 3. So you divide these by pairs. the larger one to the smaller preceding one. And when you do that, the numbers begin to converge on 1.618. By the time you get to this, I mean, first of all, the 1 settles down very quickly. Then the first decimal place settles down to be a 6. Then the next decimal place settles down to be a 1 when you do 21 over 13. Then by the time you reach the next one, this actually settles down to an 8, and so on and so on. And in fact, as you go out through the sequence, it gets closer and closer to this. At least that's the standard claim made in the books. This is, remember, this is still the story you'll find everywhere. I'm making no claims yet as to whether these things are true or false. I'm just telling you the standard story. The second part of this first part of the lecture is going to be figuring out which is true or false. So the claim is that this tends to the golden ratio, no matter how far out you go. Now, you can't prove this by doing specific calculations. You'd have to prove it by some mathematical arguments, because we're talking about infinite behavior all the way out through this sequence. So the question is, what's true? So if you haven't filled in all the questions yet, I'll give you a minute to go through those 20 questions and fill in which ones are true or false. And then we'll go through and we'll examine the standard story. Okay. This is not high stakes testing. This is as low stakes as it gets. You don't even have to show it to anybody. This is in the secret of your own hand. By the way, I've given this little quiz to very many accomplished mathematicians. Very few of them have got them all right. In fact, many accomplished mathematicians have got a surprising number wrong. In fact, if someone had given me this quiz 15 years ago, I'd have done very badly. Yes?
Question. When you say that Mozart used this ratio in music, what do you mean? I can see how a painter would use a square. How does that...
Oh, just to do with the ratios between various notes. And somehow, when he put the music together, he embedded the golden ratio in it. The ratio between notes was somehow 1.6. For example, if you go on, if you Google music pi, there's at least three composers who've composed and performed pieces of music based on the decimal expansion of pi. It sounds terrible to my ears, but you can find it on Google. In fact, there was an interesting law case a few years ago in that one of these musicians sued another one of these musicians for copyright, because they said, you know, I was the one that put pi to music. Eventually that was thrown out because you can't copyright mathematics, and it was said that the music was based on the mathematics. Now the counter argument was that, well, it was all to do with the interpretation, and that argument went through various stages of the courts. But the claim is just that in composing their music, they consciously, oh actually it could be subconscious, but the claim was that they were consciously embedding, sort of building the music so that the golden ratio was somehow embedded in it. Okay, we'll say a little bit more about that in a minute, because at least one musician actually did do that. At least we think one musician did. Okay, so there's some interesting things to look at. Okay, are we all ready to go? Okay, so let's see how you do, and as we go through, you can grade yourself right or wrong, and then we'll see what the biggest score is. So the most perfect rectangle. I mean, there's actually two questions here. First of all, do human beings actually have a favorite rectangle? Do we resonate to a rectangle that we find the most pleasing? And if so, is it the golden rectangle? The answer to both questions is no. You know, if this was a psychology class, I would know, and I don't know, but I would know how to present rectangles to you to more or less make you give any answer I want. You know, it depends on the way they're set up, on the colours, on various other things. We don't have, and this is one of these standard things you can do with first-year psychology classes, we don't have a favourite rectangle. It depends on all kinds of circumstances. So just on question 1, there is no favourite rectangle, therefore the golden rectangle can't be the favourite one. In fact, among the rectangles, how close do you think you would be to the golden rectangle if you choose one that right now you think is the most attractive? One of those rectangles is as good as I could get it to the golden rectangle. And we fooled around at the beginning to get the aspect ratio on the screen right so that this one works. Okay? So you might like to, in your mind's eye, choose the rectangle that you think is the most pleasing, if you have one. So if there's one you think, that one looks the nicest to you. Have you all got one? That's the golden rectangle. How many people thought that was the most pleasing? 1, 2, 3, 4. 4 people. Let's see, which one do I think is the most pleasing? Boy, it's difficult. I guess I would hover between that one and the 1, 2 above it, which I suspect is because I have two Macintoshes, one with a wide screen and one with a small screen. Or maybe it's the one right at the top. I don't know. I've already lost which one I want. Yeah. I wonder which. Let's see. Let's put hands up. Let's see how many. This one? Not many. That one. That one. Almost certainly nobody. That one now. That one. That one. Not many hands. So that's the winner so far. Above the golden rectangle? No. Next to it? Yeah, and that was the one I sort of liked. Above that? That's doing pretty well. The square? No one likes the square. Okay, right on the top left. Actually, no, I guess the square is top left. The total square is top left. Next to it? Ah, that one seems to be the winner, the third along on the top. Well, the second one to the left.
The second one from the left? From the right, you mean to the right?
Second one from the right, yes. Yeah, that was, I was hovering between those two, and the top right I think is too broad. So it's, it's something like that. My guess has always been that it's mostly habituation. So you ask yourself, what rectangle do people look at most of the time? And for a long time, it was the standard television screen. Well, things have changed a lot now. You could probably distinguish between Macintosh and Windows by the aspect ratios that people like. But it's certainly not the golden rectangle. Okay, so there is some preferences, but I think it's just familiarity with certain shapes. Okay, what about this one? Is there anything? Well, the way we have to play this, by the way, is the onus is on someone who makes a claim like this. The hypothesis would be that the golden ratio is embedded in this thing in a meaningful way. So the person who makes that claim has to present evidence. Okay. So the question is, for which of these claims is there any evidence whatsoever that's suggestive that it's true? In the case of and there's no drawings around. We don't have any sketches from the people who built the Parthenon. There's no sort of strong records of these things. So we have to go by just what's available. So is there any evidence for this? Well, the evidence that's presented is that people take these images and they draw the golden ratio on there. They go golden rectangles on there. But you've got to ask yourself, you know, why pick that point? I mean, I can see various points you might want to put it, but the most obvious points are not the ones chosen, which leads one to suspect that you had a golden rectangle and you moved it around until it fitted some points. So one problem is, where do you draw these things? Another question is, let's think about this. I mean, I expect everyone's been to the Parthenon is actually quite a large building. Now, if you scale up this picture to the size of the Parthenon, these rather thick-looking lines are going to be huge swathes in the real thing. So these are not lines on the real Parthenon. These are massive great areas that you would be painting in. But if you've got sort of lines that are 2 or 3 meters wide on the Parthenon, then you're going to hit all sorts of points. So there's going to be an awful lot of slack if you regard this as scaled up. So there's really nothing more going on here than wishful thinking. Doesn't mean to say that there isn't embedded golden rectangles, but there's no evidence for that. By the way, I'll give you a reference at the end to the scholarly research that's behind everything I'm saying about this. This isn't just my opinion. There's been research on this, and I'll give you a rather nice readable reference that will take you to some of that research. There's no evidence whatsoever that the golden rectangle was consciously or even unconsciously in the Parthenon. It's just wishful thinking drawn with these drawings. So that one's false. You can tick that one as false. No evidence whatsoever. So false means unproven. We're taking scientific criteria. Someone's made a claim, can they justify the claim? And if they can't justify the claim, we don't accept it. You know? We could stand to be corrected later on, but right now, this is false. Here's what's true. Euclid certainly looked at this thing. He didn't think it was that big a deal because he didn't give it a fancy name. He just called it extreme and mean ratio. Okay, so he clearly wasn't thinking of this as some cultural artifact. Leonardo da Vinci's friend, Pacioli, was the guy who gave it the name divine proportion. That's going to guarantee to give this thing some, you're in 15th century Italy, and if you call something divine, people are going to take notice. So that already gave people this sense of view. This evokes numerology and religion and all sorts of stuff. That's going to give it a life. Calling it a golden ratio, or the golden rectangle, that's much more recently. The brother of the famous Ohm of Ohm's law in 1835 wrote a book in which he called it golden. So you've got words like divine and golden and perfect proportions. I mean, people are going to love this, right? And indeed they have. Unfortunately, that's led to a whole cottage industry of people making claims about this thing. There's no evidence that the Egyptians knew this number at all. Nothing in their writings suggests they knew it. And given the massive size of the pyramids, you're going to be able to find golden ratios all over the place if you choose to. So that one we're going to have to say false. No evidence whatsoever. Babylonians, well, same thing. No evidence that they even knew the number. False. This one's an interesting one. Because if you talk to architects, they will claim, and it's in plenty of architecture books, they'll claim that you're using the golden ratio. In fact, a few years ago, I was the Dean of Science over at St. Mary's College in Moraga, and this was in the 90s when you could raise a lot of money, and I raised $35 million, that's why they hired me there, and to put up a new science building. And so having raised the money, we started to build this new science building, and I chaired the committee that hired the architectural teams. Now, the architects came in, and knowing that this was a sort of a prestigious liberal arts college, most of them had a presentation that began with the golden ratio. And at that point, that was about the time when I was getting very suspicious about this golden ratio stuff. In part because I just didn't buy the golden rectangle thing, and I actually ran some experiments on students with the same results that we had here. Okay, when there were some preferences, it wasn't the golden ratio. So when we had these groups of architects and they made these presentations, I had a couple of questions for them. And the first question was, do architects use the golden ratio? Every one of the architects said yes. Question 2, did you use the golden ratio? Oh, no, not me. But I know a guy down the road that's another architect. I didn't meet a single architect who claimed that they actually used it. Now, they use things like 1.5, 1.6, but that's by the by. There were some, 3 to 2 is a nice ratio. Okay, so there are some ratios that they used. And it turned out that they really didn't use the golden ratio. They just used simple proportions that they call the golden ratio. But it's part of this belief system that you use the golden ratio. But you can't find an architect who ever, well, actually, with one exception, you can't find an architect who ever did explicitly try to use it. Except in certain circumstances. It turns out that in the campus at St. Mary's College, you actually, with aerial shots, you can discern golden ratios that might have been deliberately put in because it was a golden ratio. I mean, it was it was a liberal arts college, and it's the kind of thing they might well build in. We actually built something into the science building I built that I now regret, because we've now embedded in stone something that I think that I now know to be false, but that's life. You'll find the same claim about the Cathedral of Notre Dame. I didn't mention that earlier, but these claims about the architecture go on and on and on. There's just no, there's no rhyme nor reason as to why you would put these lines where you put them. Ditto with this thing. I mean, you can certainly draw 3 golden rectangles on those 3 obvious vertical stacks, but you have to place them very well in order to make sure it's even close to the golden ratio. So that one's false. Okay. What about this one? No. People differ. By the way, when we use the tape measures, you don't have to strip off and do this. But we'll do the sort of the cleaned up version of this one. When you start measuring the human body, there's a whole range of variation. And even if you start to look for sort of the median figures or whatever, you don't end up with the golden ratio. This is, you get close, but 1.6 is there's lots of things that are in the ratio of 1.6. Okay, so that one we've got to say is false. There's just too much variation in the human body. You'd also have to, if you really wanted to sort of push this, you'd have to give some sort of physiological explanation as to why nature was converging around the golden ratio. And I'm not going to rule out the possibility that someone comes up with one of those things, but it ain't happened yet, and people have tried. Okay, what about in art? Well, you'd imagine that artists, if they've read about the golden ratio, might well start to embed it, but surprisingly few of them actually did. Botticelli certainly didn't. It's just all spurious, picking things wherever. It's, the golden ratio is in the eye of the beholder here. Da Vinci, no, he didn't use golden ratios. He used things like 1.5, very simple ratios. So that one's false, even though he knew about it because of his friend Pacioli. And there's also, you get the sort of picture of the Last Supper and things, you see all of the things. The question is, in all of these things, there are arbitrary choices of where to draw the lines, and the lines are drawn very thick so that it's impossible to give a counterclaim and say it's not even close to the golden ratio. So drawing thick lines on paintings is not very convincing. So no, we can't accept that. That's not scientific evidence. Here's one that I found, which is a delightful example. Well, of course, only some of them are golden rectangles. I'm not entirely sure which one. I think it's the top one in the middle is the golden rectangle. Maybe this one on its side. But you have to ask yourself, why are the lines drawn where they are? I mean, I can't find any strong reason as to why you should pick, the guy's forehead. Why not the guy's nose, or whatever? I mean, there seems to be just you started with lines and you drew them so that you'd get some golden rectangles. Well, that's not evidence. That's just numerology. That's just wishful thinking. So no, we can't count that one. What about this one? There's all of these incredible claims about this one. No evidence, nothing in writings or drawings or anything, nothing to suggest that, that there was a grid drawn in pencil with the golden ratio underneath it or whatever. So we have to say that's false. So it's not doing very well, the golden ratio so far. Most of these wonderful claims turn out to be completely unsubstantiated. Of course, artists did read about this, and there were some times when artists did try explicitly to do it. And I've mentioned a few people who tried to do it. But that was just playing with representing the golden ratio. It wasn't because of the inner aesthetics, it was just because it was a number that had some interest. There was even an exhibition called the Golden Section in Paris, but they just thought it was a cute name. It actually had nothing to do with the golden section. So, there's some connections, because artists get everywhere, but this isn't because of aesthetics, it's just because it was an interesting number they tried to play with. And more modern artists have done the same thing. This is one that I rather like, where it's just picked sort of culturally accepted representations of the golden ratio and Fibonacci numbers. What about Corbusier? Well, this is one that's correct. Here's the architect that actually did take this seriously. So we've got a true. And he explicitly tried to do this in designing cities and so forth. And he has this this figure, this sort of vaguely Arnold Schwarzenegger looking shaped man called the modular. Okay. But it looks to me more like the figure in the movie Avatar than a real person. And you clearly realize that in order to get golden ratios, that figure had to be very stylized, with a navel in a most unusual position, quite frankly. And you have to go to those lengths if you want to have the golden ratio. But it was, you know, it was an interesting thing for an artist to do, for an architect to do. Did Virgil compose it? Can we find the golden ratio in Virgil? No. No. What about music? Mozart? Bartok? No evidence whatsoever. Nothing in any of the writings or notes or anything to have indicated that. What about Debussy? We don't know. There are things that suggest that he might have done. He might have explicitly tried to embed the golden ratio in the music. It's not convincing, but it's not negative either. We've got to leave this one as a maybe. So if you said true or false for this one, mark yourself correct. Right? Or if you didn't put it in because you didn't know, you can mark yourself. But actually, everyone can mark this one as correct because we really don't know. What about this thing? What about this? This is the golden ratio in here. Well, if you go over to that science building in Moraga, you will find in the middle of this hall, there's the main science building that we built, the wet science building, the biology building. There's a big sort of rotunda where you come in with a spiral staircase going up. What was more natural than to have a shell, a nautilus shell, because there's marine biology in that building. So there was a nautilus shell that turned into the spiral staircase. I felt so pleased with that. We embedded that. The architects loved it. It looks gorgeous. It's all in beautifully stained concrete. I mean, we couldn't afford marble. I mean, even in the 90s when there was VC money flowing everywhere, marble was going to be too expensive. So it was stained concrete. It looks beautiful. And that was the time when I was beginning to be really suspicious about this stuff. Now, you can't find the golden ratio in there. Even though it's on the cover of one of my books, written many years ago. It's true that that thing is a logarithmic spiral. It's an equiangular spiral. This is a very mathematical object. Because of the growth pattern, there's a lot of elegant mathematics in there. It is a nice spiral that grows according to a fixed angle. Unfortunately, the fixed angle has no relationship to the golden ratio. It's a different spiral. So a spiral is a spiral is a spiral, but it's not the golden spiral. So it's like saying rectangles. No, there's lots of things are rectangles, but not necessarily the golden rectangle. So it's not in the Fibonacci cell. Okay. That was one of the last ones that I had to put up with disappointment. Okay, what about these? Those are all true. The golden ratio is all over the place. You'd expect it to be here because it's involved square root of 5, and you've got a 5-sided figure. So it's embedded in these, and it's embedded in some of the regular, not all of the regular solids, but it's in some of them. Here's a rather nice one where you can get golden ratios ad infinitum. Remember, these are ratios of lengths. Remember, the golden ratio is not an actual ratio of whole numbers. But if you start looking at long and short parts of diagonals and dividing them, then you keep iterating, and the golden ratio is everywhere in the pentagon. But of course it is. It involves root 5, and so you'd expect that to happen. So that's correct. Is it in Penrose tiles? Indeed it is. The first kites and darts that Roger Penrose came up with to build these things was explicitly built on the golden ratio. So the golden ratio does seem to be involved in fitting things together in an efficient way, because he had to fit things together to fill up the plane without the pattern repeating itself. And it turned out that the golden ratio was an important part of doing that. Fractals, yeah. Fractals, it's all over the place. Remember, fractals are obtained by taking a simple reproduction pattern, and iterating it. For example, you can start with a leaf, and this is meant to be some sort of a leaf growth, and you replace a leaf by 2 babies. If you look at the first one is just a single leaf, then it has 2 children going out the top, and those children are scaled down by a factor. There's a scale factor going up. then they have children by a factor that is scaled down, and then they have children by a factor that's scaled down, and the scale factor is the same all the time. Now, if you scale them down too rapidly, the thing will just peter out, like a tree that grows and then just sort of dies because there's not enough water. So if you scale them down too rapidly, it just peters out. If you don't scale them down fast enough, you'll find that they start hitting each other and overlapping. If these things are not shrinking fast enough, then they'll start to overlap. In between dying out and overlapping and making a mess, you can find a pattern where things just about touch but not quite. Guess what the ratio is that makes that happen? It's the golden ratio. The golden ratio is the difference between dying out and too much growth that you overlap. Now, that's a cute one. That's a beauty. And here's another example of these patterns. If you want to end up with this beautiful thing that looks like one of those rugs in University Avenue, in those endless rug shops that we have down University Avenue, the growth pattern, the ratio between each generation and the next, the one that makes this beautiful so you don't get overlapping and you don't get dying out, is the golden ratio. Yes?
Dumb question, but is there anything in terms of population dynamics or population biology that would apply with that? You're talking about the dying out and kind of
I don't know for sure, but that wouldn't surprise me. And there may be people in this room that could find that out, actually. Yeah, certainly if you've got a regular growth pattern, the golden ratio is in there. And as we'll see, there are connections with biology. So when you've got biological growth, the golden ratio does crop up. There are some really interesting ones to do with, trees in forests that sort of space themselves out and things. The book hasn't really been written, metaphorically on that, but it would be unwise to discount anything that involves biological growth. It's in there. Yeah.
Those fractal patterns that you mentioned that don't quite touch,
Yeah.
they will never touch.
They will never touch. They get close. Yeah, it's asymptotic. They get closer and closer. Yeah, that's right in there. Okay. And the golden ratio, for reasons that are sort of understood, is the ratio that makes that happen. I'll hint on that at the end. Okay. These guys look kind of surprising, but if you go back to the definition of phi in terms of that splitting up of a line, that's really a different way of saying the same thing. So these look kind of interesting. Actually, this one sort of explains why this occurs in biology. In a certain sense, this tells you that among all irrational numbers, the golden ratio is the one that's most irrational. Now, that's a very ill-specified thing to say, and because there are different ways you can talk about how irrational are you. And it's not a transcendental number, which is the standard way, but there are ways of talking about irrationality. If you're talking about numbers being represented by continued fractions, numbers we usually represent as decimals, but you can represent numbers as continued fractions. Something plus something over something plus something over something. And most numbers, the denominators keep changing. So this will be like a decimal expansion, except it's a fractional expansion. Then you just keep pulling it apart. And you get different numbers appearing everywhere. In a sense, when you look at all numbers as represented by continued fractions, when everything is a 1, that's sort of the number that's the farthest away from everything else. And so it's the most irrational in some sense. And that turns out to be a pretty convincing or plausible explanation as to why the golden ratio is the point where these fractals are sort of asymptotic with each other. So that one's true. I mean, those are true. The fact that these equal phi is not deep. It just comes from that equation. But this is actually to do with why these things are, why the golden ratio is fundamental in biology. Here's some interesting ones. Oh, my goodness. Oh, Lordy, yes. So it's claimed that George Clooney certainly scores well on male beauty, right? And I guess Paul Azan scores well on female beauty. And so, not surprisingly, people have imposed golden ratios on George and polar. This one was much more recent. This was actually an advert that came up not long ago. I will guarantee that's Photoshop, not a photo, and it's this actually, I took this from an advert on the web for a dentist who claimed that the dentist claimed that he would alter your teeth so that they were golden rectangles and therefore make you more attractive to the opposite sex. So, you know, if you're not getting enough dates, you maybe should have your teeth turned into a golden rectangle. It's claimed to be in drinks, to do with the ear, and you know, building sort of hearing aids and things. So you'll find these. And just 2 or 3 months ago, I was reading The Guardian online, and this was one. It's in the uterus now. So this was a couple of months ago in The Guardian. I don't know what to say. I mean, I will certainly find the golden ratio in biological systems, but simply finding measurements that match, and we'll try that in a minute. Again, we're going to use visible parts of the body, but this is just, scientific. So this was supposed to be 2,000 years of whatever. Okay. Let's look at the Fibonacci sequence. We've already seen that these are related. Actually, I better tell you, yes, they are related. That fact I made about the ratios of the Fibonacci numbers tending to the golden ratio, that's true. That one actually is true. It's been known a long time. So that was not, I can't remember if that's one of the questions, but it's true anyway. What about this one? Here's a claim. I didn't show you this claim earlier. This may be in the quiz. I don't know. You have to. Yeah. The original quiz had about 50 questions in it. I've just pared it down to 1 page for tonight. There's no shortage of claims. There's a longer list, and I can't remember which ones I left in. I don't know if I left this one in or not. Maybe I did, because this is one of the few that's true. They did do that. That was explicitly built on the Fibonacci numbers. Only the first few, because they get very big quickly, but that's good enough.
I still don't get how you can write something that's Fibonacci.
Well, you just sort of you put it on the meter and you add things together. It doesn't mean to say it sounds good, but and it's usually the first one or two, 1, 3, 5, and 8. You just add things together. Yeah, it doesn't make for great poetry, I don't think. But
How can you hear it if you're reading it? I don't think it would strike your ear as a Fibonacci.
no, and I think to make it sound good, you'd have to, you'd need a sort of someone with a really good sort of Richard Burton voice to make it sound good. Someone who can take the telephone directory and make it sound good could probably make it sound good. The same is true of pie music. It sounds very discordant, but yeah. I mean, I'm certainly well away from my comfort zone when I pass these things on, but the people who study these things say yes, this is explicitly there. Here's another one. Type of those 4 million hits for Fibonacci's, although the 1 million for Fibonacci, a lot of it's to do with predicting stock market prices, and there's all sorts of claims made about this. And here's one I found. It was a few years ago, but there's actually phi's all over the place here. Well, I'm not going to say it's wrong. I've made this claim, and there's been traders in the audience who said they do better than average by using this, and I'll believe that, because if you've got a system that you're going to use reliably, and enough other people believe the same theory, then you're going to get some order in the markets, and you can probably make some money. So, with a complex feedback system, if enough people believe something, and a lot of people seem to believe this, then you're probably going to get something. But again, this is outside my comfort zone. But I've seen nothing that makes me that's at all even plausible as to why it would have any effect on the stock market, other than a system that lots of people believe. What about in nature? There's all sorts of claims made about the Fibonacci sequence in nature. Well, here's one of them. That if you take various flowers and you look at their heads, the seed heads, you can see spirals. If you take pine cones, when you look at them, you can see spirals, clockwise and counterclockwise spirals. And you can start counting them. We'll do that in a minute. If enough people have bought them, we'll see what kind of answers we get. So the claim is that if you start counting spirals in pineapples, counting the spirals in the seed heads of various flowers, if you start counting the way the leaves appear on plants, that you'll find Fibonacci numbers cropping up. And those are all true, which means, I mean, empirically they're true. When you count them, you see that. And there are explanations, there are scientific explanations, relatively recent ones, that explain why the Fibonacci numbers occur in nature. So now we're into science. There's evidence, there's explanations. For example, if you start counting just petals on flowers, you won't always get Fibonacci numbers, but by golly, you'll get a lot of them. Fibonacci numbers are very, very prevalent when you start counting petals on flowers. Okay. I mean, this makes this a great exercise for teaching arithmetic to young kids in school, because you get them to go out into the gardens and count flowers. And it's a wonderful way of, I mean, I'd have been really upset if this one had turned out to be false, because this is a wonderful one for getting kids interested in numbers. Wonderful, and it's true. Okay, so these are okay. Look at spirals, you start counting the counterclockwise ones, the clockwise ones, you get a pair of successive Fibonacci numbers. Here's another one, beautiful picture where you can see the spirals. In the pine cones, if you start counting them, you'll find that there are successive Fibonacci numbers in these things. Okay, and here are the numbers you can get. If you start counting them in sunflowers, these are the pairs, clockwise and counterclockwise. Okay, 21 or 41 clockwise, and then 21 combined with 34, 34 with 55. So you've got Fibonacci numbers, pairs of successive ones, ditto in pine cones, ditto in pineapples, and so forth. Okay. Another example would be locations of leaves on the stems of trees and plants. Here's a more interesting one. It's interesting, you've got to sort of work on this one. You start at a leaf and you count the number of complete, if you go up a stalk of a plant, the leaves sort of come up in a spiral. Okay, and if you count how many complete turns before you find one leaf above the other, you'll call that P. And then at the same time count how many leaves occurred during that spiral. So it's how many times you curve round before you get one leaf above another, and how many leaves have appeared during the process. And then the ratio of those two things is called the divergence of the plant. I'll put a picture up in a minute. Spiral round, this is meant to be a side view and a top view, side view and a top view as you go around. And so as you go around, you've got a 1, you circle around, you've got a 2, circle around a bit more, you've got a 3, then a 4, then a 5, then a 6, then a 7, then an 8, and the next one will be back on top of the 1. Okay, so you've gone, and you've gone a certain number of times round. Okay, and if you do this, these are the kind of numbers you get. 1 and 2, 1 and 3, 2 and 5, 3 and 8, 5 and 13. Okay, not always, but these are very, very common. You know, better than chance. Okay, so, you know, better than random for sure. Right. Okay, so the question would be, what's going on here? Because this is, you know, you've got statistically significant results here. Well, this was known way back. Da Vinci, who, as I mentioned, he did know about these things. He just didn't put them in his paintings. That was known. It actually goes back to the ancient Greeks, but certainly Da Vinci knew about this. It's known as phalotaxis, study of leaf arrangements. Kepler noticed that the Fibonacci numbers are much more common. Lots of work on this done in the 19th and 20th centuries. In fact, one of the reasons when we built that science building at St. Mary's, one of the reasons why we embedded a lot of Fibonacci stuff, besides the fact that it was going to be marine biology and we wanted the Nautilus shell, which I still at that point thought was connected with it, was One of the professors at St. Mary's that was there before I was there was a guy called Brother Alfred Brousseau, and he founded what's known as the Fibonacci Society, which is a respectable mathematical society now, has been going for many years. When he retired and then died at St. Mary's, it was taken over by Santa Clara University. And Brother Alfred Brousseau was also a very keen photographer of California flora, fauna, and so he had this enormous collection of pictures of Californian flowers and so forth, which is now at the University of California, Berkeley Library, thousands and thousands of images, digital images. And so it was partly in his memory that we embedded this in this science building. But most of it's okay. The Nautilus shell is a mistake, it turns out. But a lot of work was done in the 19th and 20th centuries that nailed this down, because it couldn't have been an accident. I mean, that was just too many occurrences of the Fibonacci numbers. So it wasn't an accident. The question was, what's going on? To my mind, this is the final part of the story. The people that are in this business, there's lots of I's to be dotted and T's to be crossed. There's still questions to be answered. But the thing that I sort of liked was some work that was done by a couple of French mathematical modelers in 1993. And it really, and they sort of looked at models of growth and so forth. They did experiments in petri dishes and so forth. In the case of leaves and divergence, it was how do you optimize exposure to the sun? You know, if you're a leaf, you want to sort of make sure that rain falls on you and the sunshine falls on you. And so the thing you want to avoid if you're a leaf is having another leaf obscuring the light. So you want to move the leaves around so that you minimize the chance of one leaf obscuring another leaf. And if you sort of look at the mathematics, it turns out that just as with the fractals, if you go round by the golden ratio angle, then you minimize that chance. The obscuring of one by another is minimal when you're spiraling round by the golden ratio. Now, plants tend to have discrete numbers of leaves, right? I mean, they have one leaf or two. So when you actually start counting plants, what you find is whole number approximations to the golden ratio. So it's the fact that the ratios of the Fibonacci numbers converge to the golden ratio is why you get the Fibonacci numbers. They're like truncated versions of the golden ratio almost. It's that fact of the ratios converging to the golden ratio. So we know why the Fibonacci comes up. It's because those are the whole number approximations to the growth ratio. Okay, the growth ratio which would be optimal is the golden ratio, and there's a mathematical theory to explain that. And the whole number of approximations are the Fibonacci numbers. So that, to me as a mathematician, that was a good explanation. I bought it hook, line, and sinker at that point. And the same is true when you look at the growth of flowers and spirals. It's optimal packing of seeds in seed heads and things. If you look at the growth patterns and you can do computer simulations of this, then you find that the optimal gives rise to these spirals that count with golden ratios. Okay, and that image on the top left there is a computer generated according to a growth pattern. This is generated, and it wasn't generated to produce spirals. It's just the spirals appear because the dots are added with a growth pattern. Okay, and going back to that point I made earlier, this is really what's going on, that the golden ratio is the optimal because this number is the one that minimizes obscuring things and that maximizes efficiency in things. That's the sort of mathematical explanation. Okay, and here's why we get the Fibonacci numbers. It's because they are the growth. These are the approximations in terms of whole numbers to that growth pattern. So we know some of it. So some of it's true, and we have scientific explanations. And the nice thing about this is that it goes back to the ancient Greeks and to Kepler and Da Vinci and people. They knew, they recognized that these patterns were appearing in the physical, in the natural world. And it's only more recently, in the last 20 years or so, that we've actually had some pretty good understanding of why. So it took a long time to come up with the scientific theory, but now we have explanations. Okay, and so this is for real. This is nice. This is cool. In fact, this is so cool that we can throw away all of those other things about paintings and architecture because they're nonsense and we don't need them. This is cool. It wouldn't be that surprising. If people had embedded the golden ratio in buildings, that wouldn't be that big a deal because we're people. We can embed whatever numbers we want. But the fact that nature turns out to be a mathematician, that's cool. That is really cool. And I'll leave you with one last spiral. I have no idea what is a golden ratio. I'm sure you could find a golden ratio in there. If you're interested in some references, Mario Livio, who's an astronomer, who's written several books. He's got a hobby in sort of writing books on mathematics. He wrote a beautifully researched book. And the nice thing about this is it's based on, he went through and read all of the research literature and faithfully represents it. Well, with one exception. He actually, towards the end, he repeats something that at the time he probably thought was true, but actually isn't true. So anyone who writes on the golden ratio is probably going to make one mistake, and he does too. I'll leave it as an exercise for the reader to find the mistake at the end. But beautifully accessible book, which explains, which not only explains in more detail what I've been talking about, but will actually in the references lead you towards the literature. Okay, so what I want to do now is, did enough people bring these things? Now the hard thing about this is, and depending on the pine cone you've got, you might be able to see spirals. This one is, the spirals are actually hard to see, and they go in different directions. So let's just see what kind of numbers we get. Some of them you can count on the bottom. Let me see what I've got. If you've got a felt tip pen, you might want to put a dot on some of them, or even draw on them, because it's easy to get lost in these things. And the interesting question is, if anyone can come up with a number, either a counterclockwise spiral or a clockwise spiral that's not a Fibonacci number. Let me get the Fibonacci numbers back up. Let's get a nice representation of them. Come on, let's get the numbers up so we can see them in front of us. Come on, guys. You can't find a Fibonacci number when you want one. There we go. Okay. So those are the numbers. And I'm going to see if I can do mine. So see if the question is if you can find one that doesn't have a Fibonacci number. And if you can, then we'll pass it on to your neighbour and see if they can do a second count. But it's tricky. Let me see if I can do mine. Okay. You may have to hold it away from your eyes. Let's see. I've got 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Well, if you hold it far enough away, and you maybe need to squint, you'll see spirals. Some counterclockwise and some clockwise. And the way is to start counting the spirals, say counterclockwise. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, I've lost count. Felt tip pen helps if you start drawing them on. Now I'm not going to draw on this one because it'll ruin it. This is my standard demo model. But
was that cut in the bottom cut so that you
no, this is just.
is that the way that?
No, this is one that I just found that way. The reason this was a kind of nice one. That's why I carry this around.
Because if you look at
You might find it better to do it on the sides. You can see the spirals on the sides.
like this?
Yeah, from here you've got a clear spirals. 1, 2, 3, and if you mark one of them with felt tip, and then start counting them around, and then go all around. Yeah, for most of these things, it's easier to do it on the sides. This one is a really difficult one on the sides.
It's a problem. This time of year, there aren't very many that are closed.
Yeah.
But I did find some Minnesota.
Oh, wow.
And that,
That's going to be hard to count them, isn't it? Yeah.
Well, it's kind of
Yeah.
a spiral to it.
Yeah.
It looks like this when I start to open.
Yeah. Yeah.
I brought it. You can have it. You can see when it does open
Then
they
you.
don't touch.
That's right. Yeah. 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 This is a really difficult one to count size spirals.
Not to be destructive. Is this too damaged, do you think, because of these?
I would count them on the side. Look at the side ones.
Oh, okay.
They're much cleaner.
If I get crystal, crystal is, I got 100%. But is crystal on the quiz?
Sorry?
Crystals can be Fibonacci. Crystals in nature. That was
Oh, some of the crystals.
You didn't get the answer to that, and that was. Crystals, actually, some crystals.
Yes. Yeah. 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 Yeah.
I bet other people got 100. It was actually really fun. Are more people getting them all right?
We'll see. We'll see. Yeah.
It may only be 6, but I don't know.
Okay. Yeah.
I marked one.
Oh, you marked them.
Oh, I see that.
Anyone found one that's not a Fibonacci number?
And we're supposed to get a number that's...
It should be one of those numbers, yeah. And you can do it clockwise and counterclockwise. No, sometimes it's, but that's got really clear ones when you stand far away.
It does if you start.
But you might find it easier on the sides.
It works from the top down, but when we were trying to do it
Yeah,
from
it's,
the bottom, it's not.
yeah, it's really hard to, because the spirals are sort of epiphenomenal. You have to sort of see them from a distance. And it's not an easy thing to count.
This is really cool.
Yeah.
So cool.
Yeah.
Where do you stop? How's that one?
That's what I would call the canter.
It's definitely got a spiral when you spin it. You can see the spiral. You climb up.
Yeah, I will make a claim that there are Fibonacci numbers in there, but I'm not going to count it and find out. Yeah.
That's really cool. I went online after last week's discussion. I have an 8-year-old.
Yeah.
And I was trying to explain to her.
With kids, this is great fun. Yeah,
I thought that'd be good exercise to do.
It's great stuff with kids. Yeah, yeah, it's a great example. Whoops, someone's booked out. Okay. The spiral should be going all the way around. Yeah, it's the ones that go all the way through. Well, you don't have to go all the way, but you just the clear spiral. So you count a spiral. No, and it may not go all the way around. It depends on there. But you just got to count the numbers of them. Yeah, as far as you can get. Yeah. Well, that's a beauty. But
How did you even... Oh, got it. Okay, got it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13.
that's the 13. Yeah.
It's weird to sort of get the hang of how to count it.
Yeah, counting it is not easy, and they vary quite a lot. But once you get the hang of it, it gets easier.
Is
Yeah.
13 most common for binders?
13 is extremely common. You either get 8 and 13 if it's a small one, and sometimes you'll get a 13 and a 21.
Otherwise, you'd have to get 5. Otherwise, you'd have to get 5.
5 is so it's got to be a very small one. So 13 is the most common. Yeah. Yeah. Oh, let's see which is the best way to do this one. Yeah, this is like mine. It's hard to see it from the side, so that's okay. So there's 1, 2, 3. And let me put my finger on one to count. It's there. So there's 1, 2, 3, 4, 5, 6, 7, 8. I'm counting 8 counterclockwise. So if you go clockwise, you probably have 13. But it's 13 is very common. Yeah.
It's a bit wet in terms of tar on it. But I did get 8.
Yeah, 8. So the other one's probably 13 then. 13 is really, really common. Small ones you can get 5 and 8.
I had a question for you.
Yeah?
Now that we're doing sequencing the genomes of Arabidopsis and Fauna, are they seeing Fibonacci sequence in that side of the genetics?
Don't know. Don't know. I'm sure if you look, you'll see it. The question is whether you're seeing anything meaningful. I don't know. I don't know.
I'll ask my scientist that.
I'm always very hesitant to discount things in growth. It's an optimizer. The point is that the golden ratio is optimization, and evolution's all about optimization, and it gets in all the time because it's optimal.
You want to see? There's a jaws. There's an insect in there.
Oh, crikey! Yeah.
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 So that's. What can we say about him? There he goes. He's moving around now. He's like.
Okay.
Can we find a Fibonacci or golden ratio in that bug? Probably could. Look at insects as well, or no?
I don't know. Insect populations.
Absolutely. Or honeycomb. Well, honeycombs?
No, honeycomb is a different theory behind those. Yeah, that's a hexagon, and that's a sort of a minimization of maximum volume for the minimum material. Yeah, so it's a different piece of mathematics.
Maybe you know, there's a theory in biology. It's expulsion something, energy something. Maybe it's just expulsion. I can't remember the second word. It's basically how you never are touching anything even when you're sitting on it because of all the different atoms that
You mean physics? I mean the physics ways.
Yeah. Is it expulsion?
Because you're never, because there's so much, you're mostly empty space. We're all most empty space, so you're not literally, and with actually, you're not contacting anything, you're actually, it's the force of, it's atomic forces that are pushing, that are repelling, yeah, that's what. Yeah, in a way that.
Because then like when you ask about biology.
Yeah.
Well, that may help somebody with OCD.
Yeah, exactly.
Really, they're just pushing against.
I think I'm going to put this guy back over. I'm going to put him back. I feel like I should put him on the side. Oh, okay, good. You know, nothing to worry about in the backyard. No, the county
I'm not hopeful. Yeah.
Well, as I said, this is a wonderful thing to give to small kids in the school, right? So, and here we are. It's just, So, have I? Whose website?
I think her name's Biodell, but it's called Doodling in Math Class.
Oh, Vi Hart. Oh yes, Vi Hart. Yeah, she's got some nice things on this. Yeah. Oh boy, this is huge, isn't it? This is probably 13 and.
13, okay. All right.
Yeah, this is probably 13 and 21. So I'm sure there's 13 one way and 21 the other. I'll make a prediction. In one direction is 13, in the other direction is 21.
I only know how to do 13. I don't know how to do 21.
You have to do it the other way direction. So you can trace them one way, and you can trace them the other way. And one of those will be 13. I guarantee the other one's going to be 21. Because of that, you can represent numbers in terms of continuing fractions, and in a certain sense, the one that's the most on its own is when everything is a 1, because when other numbers come in, it sort of brings them together. It's this isn't precise mathematics; it's sort of heuristic stuff, but because everything is a 1, that makes it a very, very special one. That's keeps its distance from the other ones. And because it's a continued fraction, it sort of represents growth. It's sort of fuzzy, but it's got some understanding to it. Yeah. Okay, so we're about to take our usual 5-minute break. And while we're taking the break, got another exercise I want to do. How many people bought a tape measure? Oh, good. Okay, well, we won't take our clothes off, we won't take our shirts off. However, we can start measuring parts of the body and looking at ratios. So there's two things you can do. One is come up with interesting ratios to measure on hands and things that's about 1.6. And one of the things you realise is this is unbelievably easy to do. There's an awful lot of things that are 1.6. There's also a lot of things that are 1.2 and 1.8 and 1.9 and 5.6. There's a lot of things to measure. There's lots of sort of pointy bits and bendy bits and things. What I'd like to do is, if people can come up with really interesting ratios that are very close to 1.6. And then I'll note them down and use them in some lectures, okay? I mean, I want some, this is empirical research for me. If people can come up with interesting ratios of things in the body, so you can do this either on yourself or with your partner or whoever's sitting next to you, just measuring things, you know, like this to this, this to that, and see interesting things that come out to 1.6 or other things that come out interesting. You know, I mean, if you get something like 3.14159, which is pi, or 2.71, you can get. So we'll take a 5-6 minute break. We can use the bathroom break, but during the break, let's see what kind of measurements we can make about the body that are about 1.6. Okay, let's call the group back to order. This was way too successful. Okay, anybody got any interest? Well, first of all, the quiz. You all graded your own quiz. Did anyone get them all right? No? Okay, did anyone just get one wrong? Anybody else just get one wrong? So you win the prize. There's a prize. There's a prize. You get a copy of my book on Fibonacci. I didn't announce that first because there was always a possibility that 10 people would have got it. So you got one wrong. Anyone get two wrong? 2 people got 2 wrong. 3 people got 2 wrong. There was no more prizes, but I'm just wondering. Okay. Okay, so the people up there near the top. Who thinks they got the most wrong? No, really, who thinks you got the most wrong? Has anybody got everything wrong?
I caught that. I like internet true and then a question mark for all of us. I don't know. I have no basis.
So who got, let's say, who only got 5 correct? 6 correct? 7? 8? 7?
8.
You got 8 correct? Anyone get 8 or fewer correct? So you got?
I think I'm in that group.
You're in that group? 8? You got 8? I do have another book I can give to one of you, but I've only got one book.
The ratio of what I got wrong to what I got right is.
This may be. Let me pass that to you. This is actually the companion book to my online course I'm giving. Oh, wow. And if you only got 8 of them right, actually you might need that book. Because that's about mathematical thinking. Yeah. Okay, so that's... and I'm quite willing to bring another copy next week. You're welcome to have a copy. So I'll try to remember to bring another one next week, because you may need that book as well. It's called Introduction to Mathematical Thinking. And it's...
You hinted to us about the answer stuff. You know, that I'm sure we're going to have a lot more wrong.
Yeah, yeah. As I say, most professional mathematicians get an awful lot of them wrong because it was part of our culture. You know, we love examples that we can use to interest students, and so we love these things. You know, it's like linguists talking about Eskimo words for snow. I mean, they can't resist it, even though it's all rubbish. So, you know, of course it is. I know too many linguists, including ones at this campus in UC Santa Cruz, who, you know, point out that English has just as many words for snow as whichever Eskimo language you want to pick. Anyway, that's another issue. Measuring. So anyone come up with really interesting ratios that are really close to 1.618? What was the best one we got? You guys were doing all sorts of measuring here. Did you come up with some really cute ones? Sorry? No, Ed.
I feel like it's pretty mainstream, but it was from here to here and then from here to here.
Okay, so that length and then that length is about 1.6, you think?
Well, I divided it
Yeah.
at 1.58.
1.58. Yeah, by standards of golden ratios, that's a hit. Yeah, anything between about 1.4 and 1.8 is usually gets in with variation. Yeah.
Well, we thought, or at least I was thinking, well, it has to be for there to be a reason behind it, which is kind of what you're saying earlier. I think about the belly button. You'd think they'd be adjacent.
Yeah.
And somehow fold so that one would fit next to the other, and perhaps the digits, parts of the finger, it worked horribly. It didn't work at all. But that was
Yeah, actually, if you try to drive it by theories of growth, it's really hard to get 1.6. They're much more like the spurious ones where you measure. Yeah. Anyone got anything interesting they want to report on these measurements?
1.161.
Ah, what was that? That's
Wrist diameter to hand length.
1.161. Wrist diameter to the hand length. I would guess that varies a lot on the population, but I actually don't know. I don't know.
Never measured those before.
No. Yeah. I mean, one can always come up with one of these things and measure 1,000 people and write a paper that says that there's this sort of number coming in. Yeah.
So my height to navel ratio did come out to 1.6.
Yeah, for people it does come out close to 1.6. I mean, 1.6 is a pretty reasonable sort of ratio, right? The point about this is, if you set your mind to it and you want to show that 1.75 is important, you start measuring things, eventually you'll find lots of things close to 1.75. It's adding numbers after the fact. I mean, measuring things and then looking for patterns is, you can find whatever you're looking for.
Have you measured the iPhone, the new iPhone and the old one?
Actually, measuring Apple products is going to be interesting because there's a lot of user testing into what people like. So empirical data behind these things. I was talking to someone about the 16:9 aspect ratio of lots of things. When I started, but the point is, your aesthetics change really quickly. For many years, I gave regular lectures using sort of PowerPoint or Keynote slides. And I got to see that aspect ratio as being very pleasant. When I started doing this online course for Coursera, all their things are 16:9. You have to reset PowerPoint to 16:9. All the videos are 16:9. I've now spent hundreds of hours working on 16:9 PowerPoint slides, images, editing videos. I hate standard PowerPoint. It just looks too clunky. I've got used to the 16:9, and yet when I started, it seemed too wide. I've just habituated to it. So I'm now a 16:9 fan because I've spent the last 3 months living in a 16:9 world. I've been putting mathematics through 16:9, and I've grown to like it. We do habituate to these things, of course. So, but that's just human beings being adaptive to whatever they're living with. Okay. Any more interesting numbers that people have come up with? I'm just.
Not personal, the 90 over 60 is 1.6.
Yeah, it's close. Absolutely. I mean, because 1.6 is in there. 1.5, 1.6, 1.7. That's a nice ratio. Yeah. But.
So the ratio of the circumference of the wrist to the length of the index finger from the base of the wrist. No, it didn't come out. 1.14.
1.14. That's another 1.1 here. Yeah. The point is, once you measure something and you get a number, you can find that same number elsewhere. I think you get the hang of it. You sort of measuring these things. Okay, how are we doing on time? Okay. One little topic I want to finish with, having wrapped that one up. And this is a short one, but it ties in with something we were doing last time. Okay. And we talked last week about, we got onto this golden ratio stuff because of Leonardo. Okay, and Leonardo bringing arithmetic into the Western world. If we go back, this is the prequel to Leonardo. Took place in the Arabic-speaking world. Those traders that were going up and down the Silk Route, they were the ones that developed algebra, essentially. And so I thought I'd leave you with a little bit of a story about, the story, not a story, the story about the birth of algebra. Okay, and again we've switched. It's one of those clunky shapes again. I wish this was 16 by 9, but it's not. We got this. The background is meant to illustrate sort of parchment. This is a nice parchment background. So let me tell you a little bit about the birth of algebra, because it's a story I can tell very easily in 10 minutes. Okay, first of all, what is algebra? It's worth noting it's not arithmetic with letters, although lots of kids leave school with that impression. It's actually a different way. I might not quite finish this, but I can pick it up next time. Arithmetic and algebra, they're really two different ways of thinking. There's an arithmetical way and there's an algebraic way. And it was essentially in sort of 8th, 9th century Baghdad that this was really brought out. But it developed over many centuries, almost along with arithmetic, but a little bit delayed. First of all, notice algebra. I'll mention that algebra doesn't require symbols. In fact, for many centuries, it wasn't, at least it wasn't written using symbols. It was always done using symbols, but everything was. Neither algebra nor arithmetic require symbols. They're just ways of thinking. So music doesn't require musical notation. It's just a way of recording it. And the use of symbols is not what's characteristic of algebra. It's the way of thinking, what you're thinking about, that makes a distinction between algebra and arithmetic. Symbolic arithmetic, the kind that we've been talking about with the Hindu-Arabic numerals or other kinds of numerals, that system, as I mentioned, really goes back to India and in Syria between 200 700 CE. Was used extensively in the Arabic-speaking world in the 8th, 9th centuries. And then with Leonardo and various other people came across to Europe in the 13th century, beginning in Italy, then moving up through Germany and then westwards. And symbolic algebra, the stuff that we think of as algebra, that's very, very recent. That was in France in the 16th century. So that's really new. The stuff that we think of as algebra, the quadratic equations written ax squared plus bx plus c equals 0, that kind of stuff, that's very new. Vieta was one of the mathematicians that brought that out. And the real distinction is the kind of thinking. Algebra is essentially logical thinking, qualitative thinking, as opposed to the more quantitative thinking that's really arithmetic. So it's the kind of thinking that really distinguishes them. This was a lesson that was certainly known in the 9th century, when algebra, as we now know it, was really invented, albeit not symbolic, but it sort of got lost more recently. Because in arithmetic, what you're doing is you're calculating with numbers. Numbers are the things you're handling. Those are the things you're dealing with, because you're handling them in your mind, but you're grasping with numbers. Whereas in algebra, you're reasoning about numbers. It's a high-level form of thinking. It's not with the numbers, it's reasoning logically about numbers. And it's calculating with compared with reasoning about. That's the real distinction between algebra and arithmetic. So in arithmetic, you've got quantitative reasoning with numbers. In algebra, you've got qualitative reasoning about numbers. A key feature, and actually at this point, there's really two kinds of algebra. There's the kind of algebra that's studied in universities, which is sometimes known as modern algebra, and then there's sort of medieval algebra, which is what most people think of. So most people's conception of algebra is medieval, both metaphorically and literally, as it turns out. But the feature of that was the way you thought, and it was essentially introducing an unknown and reasoning logically to find its value, as opposed to taking the data you've got and grinding the handle and calculating. So arithmetic is essentially a forward process. You start with some numbers and you combine them, you add them, you do various things and you get an answer. Algebra, when it's applied to numbers, and algebra can be applied to lots of other things, but medieval algebra, as invented essentially in Iraq, 8th, 9th century, the feature was that you introduced an unknown and then you did logical reasoning to find it. It's a different way of getting at the answer. Instead of computing to get the answer, you reasoned to get the answer. Now that means that what most people learn to do in the algebra class, which is substituting numbers into a formula, that's not algebra at all. By definition, it's arithmetic. Okay? The algebra is deriving that formula in the first place. Okay, so if you're simply computing, you're not doing algebra, whether there's a formula there or not. Okay, for example, if you're starting to solve the quadratic equation, one way is, how do you do it? Well, you guess and calculate. Try x equals 5, blah, blah, blah. So this is one way to solve a quadratic is just guess and check. Another way is to use the formula and plug the numbers in. That's arithmetic. All you're doing is computing. The only things you're doing is computing with numbers. There's another way of solving a quadratic, which is factorizing it. You take the expression, you manipulate it, you break it into parts, and then you solve it. That's algebra. You're reasoning logically about it. You're looking at the structure and saying, we'll parse this apart into a product of two factors, we'll manipulate it. That's reasoning about it. Of course, there's calculation involved near the end, but that's essentially algebra. Now, it's a little bit fuzzy. I'm trying to draw clean lines where no clean lines exist. And algebra and analysis, certainly medieval algebra, which still exists, but I mean the stuff that was invented in medieval times, is another way of doing arithmetic. It was introduced as a way of being very efficient to do arithmetic. In fact, if you trace it back, you can find traces of algebra back in Babylonia around 2000 BCE. You look at some of these clay tablets, of which there are many hundreds, you'll find, in the cuneiform writing, you'll find what's very clearly algebra. Now, they were actually doing geometry. It was all essentially geometric reasons about determining lengths and areas of figures. And in many cases, as far as we can see, these were just recreational problems. These were done not for any application. They were almost always done for specific lengths and areas, but it's clear from the way it was done that these were meant to be general rules, general methods for solving problems. And it was definitely a form of algebraic thinking. So the idea of reasoning logically in order to determine some answer goes back a long time. And it wasn't arithmetic, it was logical reasoning. It wasn't computing. It was general patterns of reasoning about quantities. And in fact, they didn't have a number x they didn't have an unknown for a number, but they did have indeterminates for geometric lengths. So they really did have the equivalent of x's and y's. But in these cases, they were unknown lines. And they performed geometric objects, but logical reasoning. No computation, it was logical reasoning with objects. So in terms of modern conceptions, that's what we might want to call geometric algebra. I mean, I put that in quotes because that's not a recognized term. I'm not sure whether I made that up or whether I noted that somewhere, but in any case, it's not a recognized term. They did sometimes use this to find arithmetic solution to real problems by thinking of them as represented geometrically, as did a lot of the Arabic-speaking mathematicians. Okay, here's an example of a problem from Babylonia. I added the area of my two squares. This is expressed in decimal notation. They use base 60 numbers. I added the area of my two squares, 1,525. The side of the second square equals 2/3 of the side of the first one, and another 5 more. Okay, and you're supposed to compute an answer. Okay. It was really trying to solve those two equations. Two squares added together, the area of my two squares added together is 1,525. The side of the second square is 2. So that's just, in modern notation, that's what they were trying to solve, but expressed in terms of actual real squares. Instead of saying x squared, it was a square, instead of saying a second square. So. This kind of problem was also solved in the Rhind papyrus. You can find examples from the Egyptians. The Chinese did things like this. The early Greeks did things in Euclid's Elements. But if you look at the way they did them, it's hard to call them algebraic. So in a sense, the first examples of what we might, with retrospect, with hindsight, regard as algebra was probably Babylonian. But this is hindsight, looking back and saying, where can we see the beginnings of this way of thinking? And here's an example, and this is an example that occurs in many places, of geometric reasoning, where we would look at something like a plus b squared is factored in as a squared plus 2ab plus b squared. They would actually draw the figure and say a plus b, times a plus b squared is a squared plus a b squared plus 2ab. So they would reason with the geometry rather than the algebra. But it was clearly leading towards modern algebra. I mean, it is algebra, it's just done geometrically. The first stuff that we can see that was really beginning to look like modern algebra was in ancient Greece with Diophantus, who wrote a book called the Arithmetica, actually. I mean, it was aiming towards arithmetic done logically, you know. But it was trying to solve algebra. It's trying to solve arithmetic problems by introducing an unknown and reasoning logically. So this was very recognizable in terms of modern algebra. And this is around 150, 250 current era. He used letters. The official term is literals to denote the unknowns. But that's really purely notational. I mean, it's the kind of reasoning that distinguishes algebra, the qualitative, logical reasoning to get answers. As it happens, he did use letters. He also used negative numbers, as it turned out, which was kind of unusual. And he showed how to solve equations using methods known as restoration and confrontation, which sort of correspond to modern methods for solving equations. You know, add the same thing to both sides, eliminate things from both sides. Whatever you do to one side, do to another side. Things were a little bit more complicated in many cases because they didn't have subtraction, so they had to sort of get around that. But very vaguely, restoration and confrontation corresponds to moving something from one side to the other with a change in sign and eliminating like terms from both sides. And he got a bit of mileage. He solved polynomial equations and powers, including powers up to 6. So a lot of modern algebra was coming out. Okay, that takes us up to the time of Diophantus. And I'm going to stop now because we're out of time and pick up this story next week, tell you the rest of the algebra story, and then move on to another topic. And in the meantime, please keep sending in and going on to that Google site and suggesting things, because I'll try to start factoring in things that people have shown interest in. Yes? We can talk about statistics. That's already on the list. Someone's mentioned statistics, so I'll try to throw in some statistics. I'll try to meet as many requests as we can as we go through. Okay, well, I shall see you all next week and keep measuring things.
For more, please visit us at stanford.edu.